So now we're going to talk about on-node performance. Oh, I didn't. Just wait. It's not going right away. Okay, so the basic outline of today is going to be talking about vectorization, only very little. I think about 5 slides. Kind of hit a couple of points just to reiterate some of the things that they said yesterday. Cache optimization, really in the end, they only talked about cache today, and they didn't talk about cache optimization very much, cache blocking and things. So I'm going to spend more time on that. We have quite a few more slides on that. Very briefly about the Cray compiler, just to show you a couple of things or two. Alfio is going to spend more time on that. Then we're going to hit hybrid programming again and OpenMP concepts. Yes, you could say this is an overlap from yesterday, but this is quite a bit different from yesterday too. So kind of more into why would you do a different perspective on why you would do hybrid programming. And then finally, OpenMP tasking, which he didn't talk about yesterday, and it's not a very common topic, which is exactly why I thought it would be kind of cool to talk about it here. Kind of introduce you to something else that's may or may not be useful, but it'd be interesting to think about for some people. So vectorization is going to be our first point. They've talked about this before. AVX is is basically the acronym that describes the new instruction set. Its max vector length is doubled. SSD was always 128-bit. This is going to 256-bit. So double the vector length. They still do 1 vector every clock. They call it SIMD. It's a vector, so I call it a vector. They still do it once every clock, so this basically allowed them to double peak performance, right? They just made it wider, doubled the number of transistors in the functional unit, and get double the peak performance. It is also a much cleaner instruction set. This doesn't matter to you too much. It matters to compiler writers more, but it also helps with the instruction throughput. The old instruction set was really kind of, it was first designed in late 70s, early 80s, and it was kept on having various baggage. They at least cleaned up some of that, and the old one would destroy one register every time you used it. Now you don't do that, so that saves copies. So that's going to reduce the number of instructions. Current processors for both AMD and Intel have AVX. That's true, right? Yeah, that's true. So, but we're going to be talking mostly about Intel. Vectors in general are becoming more important. They hinted at this too over the last couple of days. Really, one of the main ways that a core itself is speeding up is by adding vector length or adding capabilities to the vector unit. So if you're interested in getting a higher percentage of peak, you almost certainly have to be at least thinking what can be vectorized. So vector computing is when a single instruction executes. What is it? Let's just go back to basics. Single instruction executes on a vector and data, also known as SIMD, single instruction, multiple data, right? One instruction, in this case, does 4 flops all at once. The advantages of vectorization, reducing the number of instructions that you need to issue in order to execute a unit of work. By having one instruction that does 4 things, you basically reduce that overhead to a quarter of what it was before. It exploits data parallelism. And fortunately, in much of HPCC, there's a lot of data parallelism. There has been for quite a while. Not everything has it, but when it's there, it allows the architectures to exploit it and go faster. Lower power. People don't think about this very much, but actually all of the control flow in the processor, all of the stuff to manage queues, decode, that all takes quite a bit of power. So by having one instruction that does more work, you actually reduce the amount of power it takes to execute that. So saving energy, and really energy is, and heat and power are some of the main limiting factors. And then higher peak. You know, we get 4x. Well, this was, actually, that's a little old now. You know, 4x. If you do 32-bit data, you would get 4x, and that's current gen. Actually, now it's 4x for 64-bit, 8x for 32-bit. The disadvantages of vectorization is that the code must be written in such a way that the compiler can generate vector instructions. Yesterday, Chris said, oh, you can do your own AVX intrinsic stuff. That is relatively rare in the community. You really have to have a kernel that takes a long time and have to have the ability or a reason to believe you have the ability to beat the compiler. And if the compiler can vectorize it, there's a good chance that it's generating instructions pretty well, and that you should be spending your time someplace else. But nonetheless, the code has to be written somehow in order for either the compiler or yourself to be able to vectorize it. Intel and Cray compilers try to automatically vectorize loops. And I should say, you know, Cray basically does it at default. Intel, I believe, does it by default on the Cray machines. If you just load programming environment, we have the -vec set, and then you have to add -x AVX. So as long as the things are properly set on Intel, it's trying to generate it by default. It's examining your source code to determine if it can vectorize and then vectorize it. And your job is going to be kind of get the feedback from the compiler to determine if your important loops are vectorized or not. On the flip side, GNU, as far as I know and as far as I've experienced, mainly relies on intrinsics in C to vectorize. In other words, they don't vectorize. You know, they rely on you to vectorize. On the flip side, GNU is pretty good at scalar. I mean, you've got thousands of developers out there kind of hacking on these things, and they do pretty well. Neil, you're shrugging. You're looking at it. Do you? It does vectorize? But it can vectorize. Okay, if you up it high enough, it can vectorize. So this is, you know, the different ways of preventing vectorization. Some classic things. Well, so the first bullet is what it can do, right? Simple do loop. I'm in Fortran, not C, right? Simple do loop. The bounds are known. Everything is stride 1. Stride 1 is important. You'll see that again in a couple slides. Everything is stride 1. It can load a vector of B. It can load a vector of A. It can still, even though C is not dependent on I, it can load a scalar and promote it to a vector and do all of this in vector instructions. And you'll see in Loopmark listing in a bit, nice V's. The Cray compiler will tell you pretty obviously when it vectorizes. But why can't it vectorize? Loop order. You know, if you have I, J, K, and you know, I is the leftmost dimension, the fastest moving stride 1 dimension, J is not. If J was the innermost or something like that, and you didn't have a clean stride 1, well, they don't really have good instructions for loading strided data, so the compiler may choose to not vectorize that. That might be one. Recurrence. X sub I is equal to X sub I minus 1. This is not data parallel, right? Every iteration depends on a result from the previous iteration. So normally you can't vectorize this. I mean, there's various tricks to try and vectorize it that were important on the old vector machines, but most of those tricks don't really apply to this one. You just do it in scalar on x86. Subscript ambiguities. Since in this case, I plus k is equal to x sub I, if you don't know what k is, then it might be -1 or +1 or whatever the problem is, and the compilers say, oh, I don't know if there's a data dependence. So sometimes the compiler can absolutely see there is a data dependence, and sometimes it just doesn't know. And if it doesn't know, it has to assume the worst case, and that prevents vectorization. Similarly, if there's indirection, this is nasty for two reasons on the x86. First of all, there's not really a good gather-scatter type of instruction. Gather is when you take the single words from around the process, around memory, and load it. Scatter is when you take single words and store it. They don't have a good instruction, and if they did have a good instruction, we don't know if there's repeated indices inside of this array. So that can prevent vectorization. And then really nasty one, subroutine calls. If your loop has a call to a subroutine or a call to another function, the compiler has no idea what's in there, can't generate instructions for that. It just immediately can't even do dependency analysis, immediately shuts down vectorization, almost always. And then spaghetti code and branching. Branching is if test. The compiler, and they talked about this, they have some blend functions and a few other things, and the compiler can do some tricks for very simple if tests. But if the if tests start to get very, if the body inside the if test starts to grow very much at all, and I think we're talking, more than a simple statement or two. If they grow very much at all, if they ever become nested or anything like that, the compiler is going to start to say, oh no, this is either too hard to vectorize on x86 or it's going to be too inefficient. Spaghetti code is when you really start to get complex control structures, go-tos or backwards, this or that, and skipping around. And again, the compiler probably, even if it could figure out the flow control, it would probably say, no, this is not worth it. We're just going scalar. Those are the main highlights. So if you want vectorize, you want it as clean a loops as possible. If you have some of this stuff, you can either decide, can I rewrite it to be relatively clean, or is the reality that I'm going to stick and lose vectorization and I have to look for performance someplace else. So stride matters. I don't know how many people were around with the and really got on the old Cray vector machines of the 90s and maybe early 2000s. Their stride didn't matter so much, or it was something you considered, but it didn't prevent vectorization. Well, in this, it's really pretty important to vectorization. And what we have here is some representation of memory, or some representation of a two-dimensional array, and up here, where you might index on the first dimension, the fastest moving dimension, using I, and you would increment or access the second dimension using J. Now, what always happens in this is simple Fortran, but what happens is that it basically lays out a column in memory and then moves and lays out the next column in memory. So if you were to take a row here, which is colored, you would actually see that the next colored box in the row is actually not the next position in memory. It's some distance away. This is a real problem for the x86 architecture, because basically their load and their store instructions work on a contiguous 256 bits. So if you were to do a vector load, you would load those 4 elements, only one of which is useful to you, right? And so once you get it into the vector, it might be able to do a vector instruction, but who cares? It's only one of the elements is really useful to you. Now, the Cray compiler, in some of these examples, will try and construct a vector out of some of this stuff, but it's pretty easy to imagine that the word construct a vector out of scalar loads is not the most efficient thing. And so it's either, at best, it's going to be less efficient. At worst, the compiler's going to give up and say, no, I'm not going to vectorize this anymore because it's not efficient. It's far better to access where you're incrementing the fastest dimension one at a time for every iteration. Then, when I do a vector load of 4 elements, I get 4 elements right out of memory. It's a single instruction. I work on it while it's in the register, and I store it back as a single instruction. Or in their case, maybe 2 instructions, but in any case, it's a pretty efficient process. And that is, if you ever had a vector code or a code that can trace its history back to vector machines of the 90s and stuff like that, and they were really well vectorized then, and they're no longer vectorizing now, or no longer performing as well now, this is something to consider. Now, the next slide is, we're going to get into cache, but at this point, I'll also say something about caches, and that he talked about how the caches work and spatial locality. Well, the good news is you almost always want to do stride 1 through memory because that's the way the cache likes to be accessed in the first place, right? If anytime you access 1 word, it's actually moving 8 words into the cache line. If you only access one of those, only use one of those 8, you're throwing away 7/8 of your bandwidth. So you really want to use all 7 of those. Now there's lots of, or all 8 of those. There's lots of ways to do that, but in HPCC, one of the easiest ways is to make sure that your loop is stride 1. Your innermost loop is a stride 1. So that is my vector compressed into a few slides. I just wanted to refresh everyone a little bit, and they covered it yesterday. So now I'm going to move on to caches, cache blocking, unless there's a question about vectorization or a comment that this sucks or whatever. Okay. So cache blocking from start to finish. This was actually, some of these slides was one of our guys at Cray spent a lot of time making relatively cool slides. So I don't know how many of you are familiar with cache blocking, either as a concept or have done it before. This might be a good refresher or introduction, but it's important enough to note. You know, arguably, maybe not cache blocking by itself, but the way how much memory bandwidth you use is one of the most important indications of your performance. Probably even more than vectorization still. So that's why it's important. So processor vendors, they just admitted themselves, are adding more cores faster than they're adding main memory. We can always keep on asking for more memory channels. We can always ask the memory subsystem to run at a higher gigahertz. But the fact of the matter is that Moore's law and the number of transistors on a die is increasing way faster than the number of wires that you can get to main memory or the latency to main memory or anything like that. So really, over the last 20 years, people have gotten used to using caches. The hardware vendors have been putting more and more complex and larger caches on the chip, and users have been getting used to using those caches. And one thing is cache blocking. And that is a combination of what we call strip mining and loop interchange designed to increase data reuse and thus reduce the main memory bandwidth requirements. The more times you use a data object, you bring it in, The more times you reuse it, the fewer times that it's going to get kicked out, and then you have to bring it back in. Takes advantage of temporal reuse. This is the main thing. We're trying to increase temporal reuse. I'm going to reuse it before, temporally, before it gets knocked out, right? And then good cache blocking will take advantage of spatial reuse as well. You can't only think temporally. You also have to remember that these cache lines are 8 elements long, and they're kind of very much integer arithmetic. So we can't just forget about cache lines. So there's many ways to block any given loop nest, and we're going to go over an example here in a bit. But which loops get blocked? How do I block them? When is what is the performance? You can do an analysis, and I recommend if you can think about it beforehand, that's beneficial. But in the end, also there's probably going to be some trial and error, even if you convince yourself that cache blocking on this loop is going to be a good idea, or on this loop nest is going to be a good idea. There may be some trial and error on the size of the blocking and everything. Okay, so we're going to build up a really little cache. This is your cache. This is the size, or this isn't even the cache. This is your problem. And we're going to say the cache structure for this example holds a total of, each line holds 4 array elements, and the cache can hold a total of 12 lines. All right, that's a small cache, but at least we can visualize it here. And this is the loop that I'm trying to execute. It only goes to 16 on the innermost loop and 8 on the outermost loop. And it's got a basic stencil. So it's got an I minus 1, an I plus 1, and an I, and then a J minus 1 and J plus 1. So if I click once, when I access the very first iteration, I and J is the dark red block there. And the kind of pinkish blocks are the I plus and minus 1 and J plus and minus 1. So on the very first iteration, I access 5 elements. Now, if I increment the I loop, or before I do that, to load in and compute those on those 5 elements, I actually have to load 3 cache lines. And we have a little counter down in the corner that says, OK, I've accessed and loaded 3 cache lines, right? Now, if I punch it again, I believe I'm going to increment I. So my little animation says, I'm incrementing I, and you'll see that these other lines, every so often, when I get to a new cache line, boom, I bring in a new cache line. And by the time I got to this point here, our counter has said we've loaded a total of 15 cache lines. Okay? And we've actually used them relatively efficiently, spatially. For every single one of those cache lines, except for here at the end, every single one of those cache lines, we did use all of the elements. But you'll notice that up in the upper left-hand corner, our cache size, believe it or not, our cache size is just a little too small to hold that much data. Remember, we said our cache was only 12 lines long, and we loaded 15. So when we loaded these last 3, we actually knocked out the very first 3 that we had loaded to begin with. So now, if I push this button again, I will increment J by 1. And I'm back up here. Well, back up here loads these cache lines again and actually knocks out these. Now, loading these, you'll notice that 2 of the 3 cache lines I had to reload from a higher level of memory. So I didn't have a reuse. I had to reload them. No cache reuse between outer loop iterations. That's what we would say. The I loop was too large. We couldn't reuse before we incremented the J loop. Now, if I push again, it fast forwards to I did a whole J iteration, And I loaded by the end of the second J iteration, I did a total of 30 cache line loads. Push it again. If I went through all 16 by 8, I would have done a total of 120 cache line loads. All right, and you can basically think of as cache line loads as directly proportional to your memory bandwidth that you required. So this is 120. Can we do better than 120? So we said right at the beginning, unblocked loop was 120. Well, what if we block the inner loop? And now this is what we refer to as strip mining and then loop interchange. We take the innermost loop and we say we're going to strip mine it. And we're going to do only 4 iterations at a time. And we're going to make a driver loop that drives that. And then we're going to interchange the driver loop outwards. So now the driver loop for the innermost loop is out here. It has a stride of 4. And it is driving and defining the bounds of the inner loop, which is stride 1, and basically it goes from 0 to 3 starting on I block. Okay, so we go at the top. It starts off loading 3, goes down 4, and then increments the J. And you can see now it is actually able to reuse some of the cache lines before they get knocked out. So that seems like a positive thing. Now we have a reuse on the J plus 1, J minus 1 dimension. And that's pretty positive. So far we've used 12. By the time this basically is now at the end of the 2 innermost dimension or innermost loops. By the time we do that, we've loaded 20 cache lines. And by the time we've done everything, we've loaded 80. So 80 is better than 120. That's already a good boost right there. Boost in the sense that I've used less memory bandwidth. So I'm probably going to go faster. But you can still kind of see when I get to the end of a J and I increment, I'm going to have to reload some data here. So can we do even better? One-dimensional blocking reduced from 120 down to 80. What if we iterate over 4 by 4 blocks? So this is what it looks like now. Now I've strip mined the I loop, strip mined the J loop, and I push both of their driver loops out further. If I do that, I have these lines here. You can see, okay, I go 4, I increment, go 4, I increment, go 4, and it stops. And I've loaded 12. Now, since I've completed both of those innermost loops, I'm going to kind of reset on the next I block and continue. So I'm actually getting better spatial locality here too, because remember the cache lines overlap into the previous one. So I've now kind of done 2 I blocks. I'm at 18. If I do all of the I blocks in a column, I'm at 30. And if I do the whole problem, I'm at 60. Well, 60 is better than 80 now, too. So you can see how not just one level of cache blocking is beneficial, but 2 levels of cache blocking are beneficial. So, what could go wrong with this? This is all perfectly obvious to you. You're ready to go home and try it on your code, and you're expected to go twice as fast, right? Well, I tried cache blocking in my code, and it didn't help. Why not? Well, you're doing it wrong. That's the obvious answer. It's your fault. You're doing it wrong. Just go back to school. No. Seriously, though, there's a lot that can go wrong. And remember, I said you're going to have to trial and error. The block size may be too small. The cache lines sizes, or there was too much overhead of all the loop iterations. That could be one thing. Or the block size could be too big, and actually you're still accessing too much data for the cache level that you want to block for. Both are possible. You're targeting the wrong cache level is another wrong thing. They said they have 3 cache levels. And there are people that believe you should block for the L1 cache. There are people that believe you should block for the L2 cache. And there are people that believe that you should block for the L3 cache. And there are people that believe that you should be blocking for all 3 of those caches, which by the time you do all of those strip minings really begins to explode your code. And there's no one answer as to which one you should be blocking for, but you can play around or do some analysis in their head. Perhaps you haven't selected the right subset of loops to block. Maybe this was a simple two-loop example, but if your code actually has 4, 5, 6 levels, and you did the innermost 2, maybe those were already in cache. Your real problem are the outer 2, or somewhere in the middle. Other possibilities are the compiler is already blocking that loop, and we'll show you how the Cray compiler will tell you if it's already blocking the loop for you. So maybe it was already doing it for you, and you didn't know it, and that's why you're not running faster. You were already running fast, even though you really didn't appreciate it very much, right? Another possibility is prefetching is acting to minimize cache misses. We didn't talk about prefetching very much, but the hardware, mostly the hardware, is always trying to analyze the way you are loading data. And it's going to try and prefetch, pull in data before you ask for it. Now, as long as you're not using too much memory bandwidth and you're more concerned about memory latency, prefetching can be a wonderful thing. And it can really, really work. And that might be a reason why you're not going faster. Prefetching was really working for you. Another thing is computational intensity within loop nest is very large, which is another way of saying you are doing a lot of flops and you're not memory bandwidth bound in the first place. Well, if you're not memory bandwidth bound, or if you're not cache level bound in the first place, maybe you were running at that speed and you're limited by something else entirely. All of these things, and probably more, can kind of prevent you from really observing a speed up right off the beginning. So here's a real life example, real life in the term of a benchmarker, right? NPB, NAS parallel benchmarks, MG multigrid. It's got a triple nested loop here. It's got a 27-point stencil, which we don't code up actually in here, but a fairly substantial body there, and quite a bit of loads. The global grid is a 1,000 by 1,000 by 1,000. Local grid is like just a little bit more than 256 cubed. This and a couple of other similar loops account for 50% of the runtime. This was, I don't know when this data was originally taken, but let's take it as true, right? So there is good data reuse along the leading dimension even without blocking, right? You have I plus 1, I minus 1. There's quite a bit of reuse in there, but we want to do even better. This falls under the class, well, of maybe I'm doing it wrong, because first attempt, this person blocked the inner 2 loops and left the I3 loop to go the full extent of 2 to 257. All right. Then he played around with the different block sizes, BS1 and BS2, and said, well, at unblocked, I got 531 ops per second per process. And if I tried 16 by 16, that's the wrong way. You know, this is speed I'm measuring here, and this is slower. That shouldn't happen. What if I play around with it? He was increasing his speed as he went up here, but he actually never got as fast as the unblocked version in the first place. So here is an example. He spent all the time blocking his code, but it actually went slower. And the main reason is, especially at the small sizes, he was blocking the innermost loop at only 16. And with cache line sizes of 8, he basically wasn't getting a good spatial reuse. And probably also had pretty high overhead. So if you're blocking the stride 1 dimension, be careful. Don't necessarily block too small. Be careful of that spatial dimension. It might actually hurt you. So the second thing is to not block the innermost loop, but to block the 2 outer loops. In this case, he again sweeps through different block sizes. And right from the beginning, he jumps up from 531 as the unblocked up into the 600s. But to to find the optimal was somewhere in here again, at just able to break 700. So, you know, that's kind of an example of I was doing it wrong. He thought he was going to block the inner two loops, get to really rapid reuse in the L1 dimension, and what he did was add overhead and probably hurt his spatial locality. So you have to be careful. So in another slide, in a few slides, I'm going to talk about how to know when CCE blocks as well. But the thing to know is the Cray compiler is trying to block for you automatically. And it may choose to do so, or it might not be able to do so. Even if it doesn't do so, sometimes you don't want to go through all of the trouble of recoding that strip mining and everything. And the Cray compiler allows you to play around with this via directives pretty easily. And the two directives that are worth mentioning here are bangdir $blockable and bangdir blocking size. So blockable says, and then it lists the indices of the loops that you're trying to block. In this case, it says, I want you to block the J and the K loop for me because I don't want to have to retype all of that stuff. Okay? Blocking size goes and applies to the next loop, and it says, this time I want to try a blocking size of 16. And you can actually add another one here, a blocking size here on the J loop. Maybe you want to say 8 on the J loop. Or maybe you want to, then you can rapidly play around with it of 8 by 16, 32 by 8, whatever. You can play around with things a lot faster. And also, since you're not the one actually doing the coding, a computer program is doing the coding for you, it's had a fair amount of practice. It can probably do it without mistyping a character. And so that's a nice way to test out different blocking options. There are limits on this, though, and that basically the loops that you are blocking have to be perfectly nested. By that, I mean there can't be statements. In general, there can't be statements between in this case, the J and the K loop, or between the end-dos of those two things. They got to be perfectly nested. But if you do have this in the code and you want to try out blocking and you're using the Cray compiler, don't forget about blockable as a way to rapidly try some things. And minus RM is a way to get a Loopmark listing. I'll say this a little bit later again. Alfio will say it again, and we'll probably say it again tomorrow. Minus RM, Loopmark listing, it's your friend. And it'll tell you when it's trying to do things for you. And if you add the directives, it will confirm that it acknowledged the directives and tell you that it blocked. The block size what? You do not have to mention the blocking size. If you do not mention it, we have heuristics in there to try and guess what it is. But this is a good way of playing around with it. So you could just start off by saying blockable and see what the compiler does. And actually, the Loopmark listing, whether it does it automatically or whether you do a blockable without specifying a block size, it will tell you that it blocked a loop, and it will tell you the size of the blocking factor that it blocked it. So another use of it would be, well, the loop, the compiler blocked it automatically, and I looked in there, and it said it did 256 by 16. But I'm smarter than that. I know that's way too small or way too big, or I just want to try other things. Now you can go in there and you can add blocking size to play around with it, to nudge the compiler one way or another. Again, saving you keystrokes, but still allowing you to play around with that. And all of the information is in the listing file to actually confirm that it's using these blocking sizes.
One thing that happens sometimes is that when you introduce OpenMP into some pieces of code, that might change the blocking factor. So if you are not putting any directives, and the compiler is choosing some blocking for you for the exterior code, then you move to an OpenMP code. That might change. You see in the report if you use the RM function. Then you might want to insert a directive and explicitly ask for the blocking that you think is best, or that goes for this purpose.
So that is the basic how to do cache blocking, or the conventional way of what people think about cache blocking. But there are a couple of other forms of cache blocking and cache reuse that may be just as common or more common, and maybe just as important or more important. One is the interloop/region/subroutine cache reuse. Okay, between regions, between loops, between subroutines. This is effectively bring a working data set into the cache and then crunch on it many times, reuse it many times across multiple loops or subroutines or function calls. When does this happen? Well, the common way is a lot of times people actually just get lucky. They don't necessarily, they didn't really set out to do it this way, but they actually found it natural to write it this way. And what they have, this is kind of a weather-like example. They say, well, for every level in the atmosphere, I'm going to compute every sub-grid point on the surface of the Earth. And it turns out that the working set size here of this 50 by 50 is less than the size of the L2 cache. And so if this function was relatively complex and this subroutine is relatively complex and used A, B, and C in both cases, you actually got cache reuse between these two things. Might not have been L1 cache reuse, but it was maybe L2 or maybe even L3 cache reuse, and preserve that precious memory bandwidth. So that's a possibility. And this basically says, because the working set size is smaller than the L2, well then A, B, and C are likely to be still in cache when foo is called. This is also actually relatively common in codes that are trying to scale up with a fixed problem size, strong scaling. So this can actually happen if I take a fixed problem size, I run it on 256 processors, and then I say, well, I'm going to take the exact same problem, run it 512, 1024, et cetera, et cetera. Well, every time you double the number of processors and keep the total global problem size the same, normally what happens is the working set size per processor shrinks. And it's actually possible, or it happens quite often, that it will suddenly shrink, and what used to fit only in memory now fits in the L3, or what used to fit in the L3 now fits in the L2. And a classic symptom of this is when you are drawing your scaling curve and you actually can see a super linear speed up, that you double the number of processors and you go more than twice as fast. I would say the most common reason you went more than twice as fast is actually you got better cache reuse and better memory utilization, so your processor was running faster. Maybe the communication was running slower, but the processor was running faster. So that can happen. You're damn lucky if it does. So, but it also might indicate that there's an opportunity to run faster even at the lower core count. So keep that in mind. So the next one is you have reuse, but you're not necessarily lucky. And this one was kind of the opposite. So here you, let's see if I get this right. OK, yeah, this is the caller, and this is the callee. The top is I iterate over I and j. Again, think weather. I like to think weather over every single grid point over Switzerland or something like that. And for each one of those grid points, I call foo. And foo uses A, B, C, and then the number of levels in the atmosphere. Well, inside of subroutine foo, I now have to compute for every single grid point. I have to compute something on the number of levels. But, well, these are, let's say there's a substantial calculation, but I end up incrementing over not the fastest moving dimension, but one of the other dimensions. Well, the good news is that, you know, I got reuse between the f function and the g function. The bad news is that each one of these loops is not stride 1, has no spatial locality, it's not using the L1 cache properly, and it's not getting good vectorization. So yes, I have reuse, but I wasn't necessarily lucky. I just said this. So one way to combat that, or to get kind of the best of both worlds, is to block at a high level, right? And in this case, okay, I still have my foo, but now instead of handing down a single element, I'm going to hand down a vector. Again, a vector in the mathematical sense. This block could be, you know, I don't know, it could be as small as 8 or 16, or maybe we want it to be, you know, 200. Maybe we'll put a little bit of thought into it. Maybe we'll just guess and check until we come out with the right number. But the key is that once I've blocked this loop and pushed a loop down inside, it might have taken some coding, but now I have the best of both worlds. The working set size is still relatively small, but the inner loop is stride 1 and does use an entire cache line, and vectorization is likely good. And these codes are likely to be relatively fast codes. You know, bringing in a relatively small vector, a relatively small working set, and working on it for a while. That's a good way of getting a good speed. I think that's it. So those are the main ways of getting a cache reuse. The classic cache reblocking, when you've got a nice perfectly nested loop that's all in one loop nest, or this inter-region, inter-loop thing where you're kind of thinking in terms of bringing in a data work set that's relatively small and banging on it for a while, hopefully even more than just a couple loops, you know, several subroutines even, it can happen. But when you do that, just be wary of your stride and vectorization still, because that'll be the next question on the list. Any questions about cache blocking? It is really, memory bandwidth utilization is one of the most important things. They're adding cores, they're going to keep on adding cores, and we're never going to have enough memory bandwidth. It's kind of funny because, you know, 15 years ago when I was starting cache blocking, everyone was complaining if they would just give us more memory bandwidth. That would be great. I hope they give us more memory bandwidth in the next generation. And you go 15 years later, and I tell you, the gap has widened more than shrunk. But yet still people are always improving and always figuring out ways of getting better and better cache reuse. Okay, just a couple words on the Cray compiler. I'm actually going to skip this slide because Alfio is going to talk about it in just a little bit. He'll go over the different options. The one that I'm going to point out right now and in the next couple of slides, to get compiler feedback, again, -rm in Fortran, -h list equals m in C. There's a couple of other, if you read the man page, there's a few other variations of this, RA or equal A, stuff like that. This is the main one I always use. And honestly, if someone comes to me with a Fortran or a C code and actually wants me to look at a loop, or wants me to look at a subroutine code, there's a good chance that before I even ask for the source code, I'll ask for this, you know, because this can tell me quite a bit before anything. And what does it tell you? Okay, well, the compiler generates a file by the name of filename.lst. So if your file was called bob.f90, then it will be bob.lst. Or if it's bob.c, it will be bob.lst. And at the top of it will be a legend. And this is, you can always look at the top to say, okay, what is it telling me? What are these letters telling me? We have a concept of a primary type of lettering, and then the modifiers. The primaries are, you can think of, these are bigger optimizations. These are kind of bigger transformations that the compiler is doing to your code. What can it do? Pattern matching. It looked at your loop and it says, oh, your loop is very similar to a pre-existing library that's already been tuned. So I'm going to take your loop and I'm going to call the pre-existing library with the proper arguments. Great thing, especially, I mean, the Intel guys said never write a triple nested loop to do a matrix-matrix multiply. I tell you, if you write a triple nested loop to do a simple matrix-matrix multiply and put it into the Cray compiler, you're going to love it because the compiler is going to optimize, it's going to actually pattern match it and you're going to get dgem performance. So that's a great thing to happen. That's why we have it in there. It doesn't always happen so cleanly like that. But if you see the big A, that's what's happening. Loops collapse, that's basically, it takes multiple loops and collapses them into one to make one longer one to maybe improve spatial locality, just reduce overhead. Deleted, this is, you know, if you ever write a simple benchmark loop and then test it and find out like it's 200 times faster than you think it should be, it's probably because the compiler deleted it. And it can dead code eliminate whole loops and stuff like that. So again, it's happened to me more than once, and it will certainly happen to me again. So just make sure that it didn't delete it. Cloned is another thing. It made a copy of something. Inline, this applies to subroutines and functions. It was able to see the subroutine, see the function, and it says, well, it's small or it's a leaf routine. To save the calling overhead, I'm going to inline it. And then you're going to see a big I right next to that call site. Multi-threaded, that probably doesn't apply as much as anymore, but parallel and tasked, big P, that applies to OpenMP loops. If you have an OpenMP region and you actually want to make sure that acknowledge the OpenMP directives, then you're going to see a big P next to that region. Big V, vectorized, that's pretty easy to understand. Big W is unwound. Unwound basically says it saw the trip count of your loop, and it saw that it was small enough that it just replicated it that many times rather than, and blew away the loop structure. Modifiers are atomic memory operations. That applies to PGAS more than anything. Blocked is what we just talked about. It blocked your loop. Fused the loop. It fused the loop. It actually can fission your loop sometimes too. I try to get them to do this, but it doesn't put a small f next to a loop that it fissioned, but you can find it in the messages. Interchanged a loop. Partially, conditionally, or computed vectorization. Basically, this means that it often happens with a big V, and if that happens, it means, okay, I vectorized it, but it's not really clean. So if you can figure out why it's not really clean and you can clean it up, there's a chance that it'll go faster. Unroll, short loop, array syntax, and then another unwound there for some reason. So this is what our loop of multigrid looks like. And it has two loops. There's the stencil inside. There's actually an inner loop here. It's 3 loops total. Inner loop here, and then 2 outer loops. And the compiler, what it did on the inner loops, it vectorized and unrolled. So that's good. And on the outer loops, it blocked. Okay, and we see a small b. Now, this doesn't tell you a lot of information. Well, in a way, it tells you a lot, but it doesn't tell you everything, right? You know what happened to these loops. You know that it vectorized. You know that it blocked. Okay, that was all good. I can scan my code very rapidly, and if I know in my code, if I'm familiar with the source code enough that I know where to just jump to mentally, you can see if it's doing something there. At the bottom or at the end of the subroutine, then you're going to get messages that are basically is what's creating those letters. And there, you know, the loop starting at 29 was not vectorized. It will tell you if it can't vectorize it. Or loop starting at 9 was blocked with a block size of 4. There it tells you a block size of 4, and you can choose to say, well, 4 is a good idea or not. And then other things was not vectorized because it even tells you why I think it couldn't vectorize it. What a recurrence was found. Other things it will tell you, oh, this was vectorized and this was vectorized. So these are the messages that are driving the letters. If you see the letters but want more information or don't know what's going on, go down and look for the messages. So I'm probably running long because we're just starting on hybrid programming, but any questions on that? Otherwise, Alfio will cover it too later. So hybrid programming, Michael, that was his name, I think. I'm not very good with names, sorry. He talked about hybrid programming. I think it was a good talk. It was an interesting talk. But I'm going to give you a little bit different perspective on hybrid programming. One of my slides, in theory, has the same title as his. What is hybrid programming? I think I have a later one. Why do it? Well, hybrid programming is the use of 2 or more parallel programming models to scale into higher processor counts. That doesn't limit yourself to MPI and OpenMP. You can say MPI and P threads. You can throw in PGAS, which is one-sided languages. So, but it's trying to attack it with two or more programming models. Most common form is MPI and OpenMP. In this case, OpenMP is used to scale to 2 or more PEs in a shared memory domain, and then MPI is used to communicate with those ranks or those groups of PEs. 2 programming models often means twice as much work. Now, probably someone on the OpenMP committee would say, no way, it's not twice as much work. Well, really done well, it can be a substantial amount more work. So why would I want to do this? Why don't I just take that exact amount of time and effort that I put into OpenMP, and I should put my effort into MPI, and I'll end up scaling twice as high anyway, or something like that. And honestly, I would say that this was considered in the late 90s, and SGI certainly pushed OpenMP quite a bit in the late 90s. They actually pushed OpenMP by itself in the late 90s. But relatively few did it, and I think there were good reasons why I didn't do it at that time. But more and more, we're hearing people looking at doing it again. And I think just the fact that Intel said that this was important, it kind of indicates that they're hearing the same thing. More and more people are doing this. So why do hybrid programming? Well, one reason why is that it might be difficult to scale MPI to very high core counts. What is very high core counts? Well, it's higher than what you currently comfortably scale to. So if that means 256 or if it means 256,000, it doesn't really matter, right? It's wherever you're having problems scaling MPI, maybe you've reached that point. Reasons for that, well, surface to volume area, surface to volume reasons. If you have a decomposed problem and you need to communicate on the surface of whatever's local, as you take a fixed problem size and scale it up, that shrinks, and the volume, the amount of compute inside that local region shrinks at a rate that is faster than the surface area, which is analogous to what you have to communicate. Message size, I blew there we go. Hit it, right? Make sure you don't read ahead. Message size issues, that can be another thing as you scale up. Your message size shrinks. Maybe that's a good thing. Maybe that's a bad thing. It used to be more important, I think, on some of our older machines. Gemini and Aries, it's pretty good, but still can be an issue. Some communications scale as log P. They continue to get a barrier, for example, does no useful work, but it takes longer and longer. Running out of parallelism may be another one. Maybe you did a 1D decomposition to implement your MPI, and now you're just flat out of iterations to decompose. But there's still a bunch of work to be had. OpenMP may be easy or have different scaling properties. That's another reason. Actually, it's pretty easy to add OpenMP directives. And if it's obvious and you can easily do this, boom, 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 maybe you can do this. Maybe it takes you a week or two. Maybe it takes you longer. But it's might be a lot simpler than really trying to get the MPI to go any higher. Maybe it can attack a different level of parallelism. So sometimes it can parallelize over levels in the atmosphere where there's just no way that you're doing that in MPI. Or you have a 2D decomposition, but you have a 3D problem, and the third dimension is just sitting there on most of your loops. Fewer fatter ranks may increase the message size, may also help with the surface to volume ratio. And then maybe sometimes you can get clever and use OpenMP to overlap communication and computation. And I'm not just talking in the sense of I send and I receive. Both myself on one code and just a couple weeks ago, again, I heard someone else with another thing. I mean, they just take one of the MPI threads and said, you're doing communication, everyone else is doing computation. When you're done with communication, join in the fun on the computation. And they got a great overlap that way, and scale really well. So really what you're looking for and hoping for is the combination may scale higher than MPI only. I think that's, if you're scaling high enough with MPI only, then there's probably not a reason to do it. But if you're looking to scale higher and MPI is given out on you, this might be a way. Why wouldn't you do this? Well, it's more work, and you have to think about both levels of parallelism. Yesterday, he talked about actually doing MPI calls inside of OpenMP. I don't know if I would recommend that or not. It's a way to do it, but if you do it, you have to think about it. If you don't do it, you have to think about how else you're going to attack the parallelism. So you need to think about this. Again, some people just absolutely believe MPI is the only way to go, and your effort is better spent doing that. You can agree or disagree with that. Another thing is, remember, OpenMP does not repeal Amdahl's law. Assuming everyone knows what Amdahl's law is, if you've got a serial region and you are not scaling because that serial region is becoming a larger and larger portion of your time, and you cannot attack that with OpenMP, it's not, you're not going to magically run faster on that serial region. So another way of saying it is, you might have to put OpenMP in a lot of places. You can't just put OpenMP on the 2 or 3 or 4 biggest loops, because that might be only 60% of your time. And the other 40% is going to be running in serial. So that's going to really drag down your OpenMP scaling. And if you're running out of parallelism, you're running out of parallelism. There's not much to do with that until you find more parallelism. And another thing is, OpenMP does not do well beyond a die. A die is a socket on Sandy Bridge. But really, non-uniform memory access can cause real problems. They talked about doing OpenMP across the node. Be careful, right? I rarely see that as even a fruitful exercise. It is, I think it's far better for you to start and think about OpenMP on a die in a uniform memory access region. If that is working spectacularly well for you and it's doing well for you, go ahead, go across 2 dies and everything. But you're going to introduce a whole host of problems, the least of which is doing that first touch thing that they talked about. Keep that in mind. It's got limited scalability. And even if it goes beyond a node, or even if it goes to the full size of a node, that's it, right? I mean, it's not going to magically OpenMP across a half a dozen compute nodes. So briefly go over to OpenMP concepts. He ran over this pretty well. It's an API. It's a bunch of directives, compiler directives. It's portable. It's a pretty good standard. I don't know if it's an ANSI standard or not, but it seems pretty familiar. You can go to the web. You can find cheat sheets. It's pretty common, pretty well known. MPI is not meant for distributed memory parallelism. Like I said, SGI in the late 90s, they were really promoting OpenMP across their CC NUMA architecture to dozens of processors. I don't know of anyone that's trying to do anything like that right now. It's someone can correct me, but and certainly it's not possible to go beyond a node on Cascade. So it's not necessarily implemented identically by all vendors. So keep that in mind. If you stick to the common things, that's probably similar, but it doesn't even mean that they have to do exactly the same scaling or exactly the same scheduling, and performance may be different. And it's not a guarantee that if you use it, you will go faster. It will be the fastest. That's not a guarantee. Nor is it required to check for data dependencies or check code sequences that are classified as non-conforming, right? You still have to do the programming. It's putting the weight on you. It's not like you're just kind of giving hints to the compiler and expect the compiler to automatically still generate correct code. You can have race conditions in there. Important directives. The most important directive is the OMP parallel do with a private clause and a shared clause. It basically says you've got a do loop, you've got a loop, you know it's parallel, all the iterations are parallel. I put a parallel do in it. You're giving it various hints about what variables are private, what variables are shared. I'm not going to go into when is something private and when is something shared. That's a half-day tutorial by itself. But this is the most common one. The second most common one is a cousin of this, which is you start up a parallel region and then you have a series of OpenMP do loops in it. And this is just shorthand for that. But this is one of the most common ones.
You can add that we have a tool that helps in putting the directives that we show the review can help you.
Yes. Yeah. Reveal can help you with this. And I've never done that, so I'll be anxious to see how it does. So see what it looks like. Now, okay, yeah, that was a really, really short thing on the OpenMP basics, right? I'm going to start going off into not the weeds, but into some OpenMP things that maybe you guys haven't dabbled with as much. One is nested multi-level OpenMP. This is an OpenMP parallel region inside of an OpenMP parallel region, and that each level, new threads are created. Normally, at default, what it does is it just recognizes the outermost level, and if it encounters another OpenMP level inside of that, it ignores it. But you can use environment variables to turn on levels. You can use environment, and there's a bunch of environment variables that I'm not going to go over, but there's a bunch that say how deep and how often you spawn. I will admit that I have tried to use this, and I find it rather not confusing, but rather restrictive and not exactly flexible in the way you need to be flexible. For example, if you do, you would say, well, I got to do a 2 by 2. That means that every single time you hit a higher level, you'll spawn 2 threads, and then when you hit the lower level, you'll spawn 2 more. That might be great if you have an OpenMP of 4 wide, right? But if one part of the code has 1 level parallelism and one part of the code has 2 levels of parallelism, that means one part of the code will always be screwed, right? Because one part will use 2 and the other will use 4. Or if you just do 2, then they'll do 2, and this one will not use the lower levels. So that's one example. Another example, it's nice when you have a power of 2 number of processors, because then you can just keep on doubling or something like that. But what happens when you, say, have, I don't know, a future processor might have 9, just to pick one that won't actually happen. But 9, and not 9, let's pick 11, right? Well, how do I get to 11 threads with, multiplying 2 numbers together? That doesn't work out. And it doesn't have to be as weird as 11. 12 is 1. And the way the standard was set up, as far as I can read it, it actually says every single letter level, I spawn this many more. So it's like 2 by 2 by 2 or 3 by 3 by 3, but how do you get to 12? Now, we've added some environment variables to help like that. You could do 2 by 6, for example. Nonetheless, it seemed to be less flexible than what is needed. So now I'm going to introduce you to something that's OpenMP tasks inside of parallel regions. And OpenMP tasking is another way of doing nested parallelism. And I found it to be both more and less natural way of doing OpenMP programming. More natural in some cases, less natural in other cases. But we can work through that. Just a couple of environment variables. People should know OpenMP threads. This sets the number of threads that your job is going to do. You know, set it to 8, for example, if you're going to run on a Sandy Bridge die. Stack size is something you also have to worry about. Now we keep going. Okay, a new feature. New in that it's only been in the standard for like 5 years, which means that people are going to start using it soon. A task is an explicit region where you're saying that execution can be deferred and or executed in parallel with the surrounding region that is in the same OpenMP parallel region. So OpenMP parallel region encompasses an entire region, and then a task might be a sub-region that says, oh, this task can be executed at the same time as everything else. Completion is guaranteed by when you hit the end of the parallel region, the task is done. And no OpenMP threads, whether they participated in the task or not, can go further than that. Like I said, must be contained in an OpenMP parallel region. The thing is that normally you're not just starting one task, but there's some type of control flow that's going to start more than one task. And these tasks are, quote, put on a queue, and literally put on a queue, and will be executed later. Later might be immediate. That's one way to implement it. And it might be immediate because there's nothing in the queue, but it's done at some time, and you're not too sure when. And any thread in the same parallel region that is sitting on a sync point can actually grab a task off that queue. So if you have some threads, if you have a number of threads, and it's coded so that you know they're in a barrier, even if they're in a barrier in another routine, if another thread or a group of threads puts a task on the queue and someone is in a barrier, part of that barrier is actually checking, is there anything there? Is there anything there? And it can grab stuff off of that queue and start executing. And we're going to use that later. So parallelizing quicksort. Quicksort, hopefully people are a little bit familiar with. This is sorting a group of numbers from smallest to biggest, biggest to smallest. It's a good way of doing sorting. It's been shown to do pretty well in most cases. But it's not exactly very easy to parallelize. You kind of break the list, and you partially sort the list, you break it into subgroups, and then you do that. Well, could we parallelize this with OpenMP? Before I go any further, this is not about writing a better sort. I know how to write better sorts, but this one is going to be a good example of how to do it. How to use tasking. So if we didn't have tasking, if we had nested parallelism, how would we do this? Well, we're going to call the quicksort kernel. It's a recursive subroutine. And then inside of that, I do some work to split it into a left hand and a right hand, or upper half, a lower half. And those can be done in parallel. Well, I can do those in parallel by having the standard parallel sections. And the parallel section says that this section can be done at the same time as this section. If I had nested parallelism, then this is called once, and each of these is recursively called again, and then another section can split it again. And so if I had a 2 by 2, for example, nested parallelism, by the time I'm 2 levels deep, all four threads are occupied. But as I keep on going deeper than that, it's going to be ignored, and those 4 threads are now fixed. And I plot this. Now, this data is old, but it's still relevant because really the point is that for some things, it really didn't work out. They were just too small. But even a lot of them, as I went to 2 threads, I didn't get a very good speed up. 4 threads, not really good speed up. The best speed up, interestingly enough, wasn't even close to the longest list. So as the work got larger, my parallel speed up did not improve. And why is that? Well, load balance is one of the main problems. It was a very fixed way of doing the problem. Once I got those 2 levels deep, however those levels were split up, that was it. I mean, that's all the further parallelism. If they weren't split up evenly, then one guy was going to take longer than everyone else, and I was going to be limiting. Best, really, that I got was 2 out of 4. What about using OpenMP tasks? So here I have the subroutine call again, and this time, what I'm going to do is I'm going to call the I'm going to call the main sort kernel by putting in an OpenMP loop and putting a master around it. Now this says only the master call the main sort kernel, and everyone else has absolutely nothing to do and is just going to go and sit on the barrier that's implied at the end of the parallel region. The master is going to go in there. It's going to have to do some work on the first iteration, first level, but then it's going to get to the calls of the left end and the right end. And if I put an OpenMP task and end task around each one of these, all right, this basically says this can be done in parallel with everything else in the parallel region, which is everything else. And this can be done in parallel with everything else. So the master is going to put this on the queue and put this on the queue. And then it's going to go and hit the end of the subroutine. And actually, the implementation says wait at the end of the subroutine. Wait on a barrier. So as soon as it puts these guys on these calls in the task queue, the guys waiting at the barrier says, oh, there's something in the queue. Grab it. They're going to go jump into the routine, do a little bit of work, go hit these calls, see there's task regions, put them on the queue. More on the queue, more things are sitting on the barrier. They say, oh, there's work for me to do. Keeps on going, keeps on going, keeps on going. And you're going to keep on putting tasks on the queue until that queue fills up, and then they're probably just going to execute the data as well. You can also use if test in here to say, well, if the work is too small, don't continually put it on the queue until the very last element. But the point is that even if there's, as there's more parallelism, it continues to attack more parallelism. Even if one of the tasks ends up with a short list and gets done, what's it going to do? It's going to go back to a barrier, and it's just at the barrier going to look on the queue again. And someone else is putting tasks on the queue. So there's a lot more parallelism to be had here, and it kind of naturally load balances itself. So here's the parallel speed up now. The smallest ones, they slowed down, but now I took it to 2. And really, for these larger problem size, I was getting above 1.5 out of 2, and that ain't too bad. Out of 4, several of them were getting around 3, 2.5 to 3, not quite 3.5. Again, much better than the previous slide. Now this. Yeah, these are the size of the list I'm sorting. So as I go down the list here and switch colors, the list itself is getting longer and longer. Now, to me, I was originally expecting the longer the list, the more work I had, the better opportunity for parallelism and parallel speed up. And on the last slide, that wasn't the case. But on this slide, there does seem to be a trend here. This is only sorting 5,000 elements, and we are getting 2.5. And I think every list that's larger than this gets a better parallel speed up. Now this data, you can tell how old it is because actually when I went from 4 to 8, that was going from the first socket to second socket of an AMD. So it's relatively old data, but I think the point has been made now. If you have this opportunity to use nested parallelism and there may be load imbalance, think about using tasking. Now, I don't want to just show you a toy. I want to say that I did this in real life. It was a benchmark, and the rules of the benchmark procurement, we often have rules, right? or goals. And in this case, there was a rule that says the benchmark will run in less than 480 seconds or you cannot bid your machine. Period, end of story. And so the struggle was, how do I get to 480 seconds? And it turned out that the way they gave us the problem, there was limited MPI level parallelism. It was a 1D decomposition for a weather problem. And the weather problem that they were using did not use enough latitudes or whatever. And so we could not use enough parallel processes to get down to 480 seconds. If we tried to increase the number of latitudes, all we would end up doing was increasing work, not reducing runtime. There was OpenMP code, but it turned out that the OpenMP was at a high level and over exactly the same level as the number of MPI ranks. So as you increase the number of MPI ranks, you decrease the amount of OpenMP parallelism available to you. But furthermore, there was load imbalance between these different levels. So it was just not scaling very well. I mean, it was scaling to hundreds, but we needed it to go higher. Are there other levels available? Are there other levels of parallelism available? Yes, but not everywhere, and it was not uniform. Actually, I had just played around with tasking, and I was like, hey, maybe I can use it. So I won't go into exactly all the things I did, but the point is that, yes, I did put OpenMP at multiple levels. Sometimes they were on loops. Sometimes they were on regions. They were splattered all over. They weren't everywhere. But the net result is that we were stuck at 520 seconds before I did OpenMP tasking, which is larger than 480 and might as well be infinity in this case. And so, but afterwards, we were at 420 seconds. Tasking actually ended up helping both large and small core counts. It helped large core counts because it was more load imbalanced, and small core counts probably because it was just better efficient, also load balance and all the way around. We modified only about 4 to 6 files out of the 40 that were available. So we didn't put it everywhere because OpenMP was already in there at a high level. And we didn't make any modification to the existing OpenMP directives. This is all underneath. So I have a little bit more on that stuff sometime. But the point is it can be used, and it was used in the case where there was nested parallelism. So I would say the pros and the cons of tasking. The pros, it was a more dynamic use of resources. It was really natural to program in some ways. If I had a thing that was obviously parallel and could be done at the same time as another piece of code, wow, it just fit right in there. Many levels of uneven nesting, it worked on that beautifully. The cons were the directives were cumbersome if you had a loop parallelism. If what you have is loop parallelism and what you want to use is OpenMP parallel do, and what you need to use is tasking, you actually have to transform that loop, kind of package it up, strip mine it into something that you can put a task region around. So that was kind of cumbersome. Tasking is slightly more overhead, so you have to be careful about how small of a work area you're doing. And then really, I could see that it could even be more powerful given more control over how to do tasking. So, hour and 23 minutes, 7 minutes less than what I was scheduled to do. So that is tasking, and in general, that's 2 or 3 areas of on-node performance. Vectorization was a bit of a review from yesterday. Cache blocking and cache reuse, good refresher course. They didn't talk about much, so hopefully that helped. OpenMP hybrid programming, I think it's certainly something to consider. I've talked to a couple of you that have used it. And then tasking is something you might not have heard before. So if it was cool, I hope you think it was cool. And maybe someone will use it someday. But any other questions? about these on-node techniques or any other on-node techniques, or anything the Intel guys said and you disagree with.